In this video, I'm going to talk a little bit about what we are doing in Bucksburn Academy with the concrete pictorial abstract approach to teaching maths. The three stages I've got are described by the three statements here, and sort of represented by the three images I've got below. The concrete stage is all about using hands-on manipulatives to represent ideas. This can be done with lots of digital tools, but I personally feel the hands-onness makes the processes you teach more tangible with actual touch and feel. At the concrete stage, you need to be careful with your problems. You need to make sure that they are manageable. You don't want pupils getting bogged down with piles of tiles or counters. It's all about developing the underlying understanding at that stage. The pictorial stage, that's like a bridging stage. It allows for more complex problems and more unwieldy problems, but it's still giving them a strategy they can fall back on. It sort of bridges the gap between the concrete and the abstract. The abstract, that's more of the traditional thing you'd expect with formal layout and formal notation. But the CPA approach, like I said, is all about building up your understanding. You would hope pupils progress from concrete to pictorial to abstract, but one of the real strengths here is having things that you can then fall back on. So dropping back from the abstract to the pictorial, or the pictorial down to the concrete. The first thing I would show you is some directed number work with two-sided counters. Maths is all about axioms and truths, so when we introduce the idea of directed number, we introduce the two-sided counters. The counters have a yellow side and a red side, and we would be telling the pupils that the yellow side of the counter represents +1, and we would tell them how that should be written. And the other side, the red side, we would say that represents -1. We tend to hammer home the notation, so get them to pay attention to where the negative symbol is, so it's not mistaken for subtraction. This early stage of working with negative number, there's still an opportunity to use formal language, letting pupils know that -1 is a number, whereas -1 is an operation. The key concept with the counters is the idea of the zero pair. So when we add a positive and a negative counter together, they combine to give us a zero pair, i.e. as a total value of 0. And we would build up our understanding by working with problems like we've got on the left there. Here the pupils have been asked on the left-hand side to do -6 + 4. And the way we do addition is we physically build the problem. So the top box here, I have built -6 with 6 red counters. I've then added 4, I have added +4, and then I'm keeping an eye out for these zero pairs here. I know they have a value of nothing, so I remove them, and I see that I'm left with -2. So we would spend a lesson on this. We wouldn't necessarily spend a lesson recording lots of formal notation. We would just get the pupils used to the idea of the zero pair. When we move on, we would then move to the pictorial approach, which is what we've got in the center here. So again, pupils with some problems there. The first box is sort of emphasizing writing negative numbers without brackets, just emphasizing the fact that we want them to write their negative symbol high, just so we don't mistake it for a minus. The pictorial approach seen quite clearly here. Instead of piles of counters on the desk, the pupils are representing that with little diagrams, and then scoring off their zero pairs to get their answer. The next stage would be then abstracting from that, wanting pupils to approach calculation the way that we might as maths teachers approach this. when I see negative 35 plus 22.5, I know the answer is going to be negative, and I know that it's going to be the difference between the two values. It's a very difficult abstraction for pupils to make on their own if they haven't seen it with the counters. Abstract and pictorial, I mean, we can sort of flip and flop back between them. Here down the bottom, I've got these two examples here of 14 plus negative 11, and the pupils aren't drawing individual counters, so they're sort of abstracting on their own using these methods. So it's maybe more abstract than pure pictorial. But I mean, this is the whole point in CPA, is to give them something to fall back on, or to give them strategies that will help them with things that they may find difficult. We would move on to some subtraction. The subtraction sort of ties in with the addition, with the directed number work, and that the counters work best when we just focus on adding. So rather than thinking about how can I minus something, we think about it in terms of the additive inverse here. Now, this isn't teaching pupils to rethink how they do 5 minus negative 2, but it is helping them with these typical problems like minusing a negative, or even if I've got negative 5 minus negative 2, that's the sort of thing that pupils can make mistakes of. Think of the gradient formula at National 5 and how often mistakes are made in the substitution there. So we introduced the idea of the additive inverse, this idea that to minus negative 2, we add positive 2. And we wouldn't dive straight in with this. We would do a bit of work just establishing what a zero pair is and what the additive inverse is. And we found that pupils do struggle to make the jump initially, but once they make this jump of using the additive inverse, it really helps them with their directed number arithmetic. Here we've got two examples of how pupils would be approaching it. I've got pictorial, so a worksheet that we have used here, and how we would approach it in terms of abstract. This idea of negative 13 minus 14, that's me starting with negative 13, and I'm adding more negatives. This idea that it's going to give me a bigger pile of negatives. The second one, sort of introducing the idea of zero pairs and just thinking about how much more I've got in terms of these positives. Notice the lack of concrete here. You don't always need to go back to the concrete stage. If your pupils are getting on well with the pictorial approach to adding, then you don't need to go back to the concrete. I think it's also worth noting here that the CPA approach doesn't fix everything. We haven't found that it's a 100% success rate for all pupils. The bottom couple of rows in the pictorial worksheet here, you may see that there are several attempts at a couple of the questions that pupils haven't got it right the first time. And I think as long as you're happy accepting that, then the CPA approach can be quite useful. Now, the reason that we use directed number, we do directed number in this way, is it sort of ties nicely in with how we approach linear equations. So on the left-hand side, I've got two examples that I would have used in the past with my classes, showing them how to solve these level 3 equations. I would talk about balancing while I was solving these, and talk about doing the same thing to each side. And then the pupils would potentially get on with the exercise on the top right there. However, even in this top exercise, this last question would catch them out because, it's a different format from all the rest. And when we look at the questions in the exercise below, having things written in an odd order, the variable has come second, or here I'm dealing with a negative variable in the inverted commas wrong place. really, when I teach like this, or when I have taught like this, I'm not really teaching the pupils how to solve equations. What I'm really doing is I'm sort of getting them to recognize a pattern. So their understanding on how to solve an equation is limited. So what we use, or what we have been using, is the algebra tiles. Now these are a lot like the two-sided counters, in that we have a little bit of cardboard in a square that represents 1, and on the back of it, you've got -1, that yellow and red colour being consistent. And when we add +1 and -1, we get a 0 pair. We then introduce the concept of x. Now, the 1 and -1, they have an area of 1 because they are literally 1 centimetre by 1 centimetre. The x's are 1 centimetre tall, and you'll find that this yellow will fit on the end of this green. But when you try to put yellows along the top of the positive x, an exact amount doesn't fit in. So you introduce the idea of this top is a unknown quantity. We could call it x. X times 1 gives this a value of x. It gives it an area of x. On the flip side of your x, so you can literally flip it over, and it's got a red on the back to represent -x. And again, a 0 pair. The x square is literally a square where each side is x long. Your green and red x tiles will fit along the edges. So you're helping make that connection between the geometric square and the numerical square. And again, for every x squared, there's a -x squared on the back, and we can create 0 pairs. And this would mean we can start by solving some basic looking equations, but there's lots of opportunity to bring in some, not advanced, but to bring in your negatives really early. The two-sided counters, the algebra tiles, make the negatives almost trivial. So I would start by telling pupils, I'm not telling you how to solve something like x plus 1 equals 3, where the answer is obviously 2. I'm teaching you how tiles and how equations actually work. And there are a number of ways you can demonstrate this. Here I've got tiles that clone on my whiteboard, but there are a number of websites, and the website I tend to use is the MathSpot website. So here I have Googled MathSpot algebra tiles. Top result, we've got our algebra tiles here. I'm going to put some axes on to represent the two sides of the equation, but you don't necessarily need to do that. So my first equation was x plus 2 equals 1. So I've got x plus 2, and that is equal on the other side to 1. And obviously before we do this, we'd spend some time just building expressions with the tiles. But here I'm solving an equation. And I suppose the golden rule of equations is whatever you do to one side, you must do to the other. The whole point in what I'm trying to do is to get this green tile on its own. I'm trying to find the value of it. So I need to get rid of positive 2. So I'm going to add on negative 2. I'm going to add on its additive inverse. And if I do something to one side, I have to do the same to the other. Next stage would be tidying up your 0 pairs. This is why I like this website, because when I drop a -1 on top of a +1, the 0 pair quite literally disappears. I've tidied up on the other side. Now we can see here that x equals -1. My second one, that was 1 minus x equals 3. So I think of that as 1 add -x equals 3. Again, I'm trying to get the x tile on its own. The additive inverse of 1 is -1, so I add -1 to each side. I then complete the calculation by cancelling my 0 pairs, and I've got a green stick on its own. oh, it's the wrong colour. The green is on the other side. And I would be asking the pupils here, well, what do I need to do to turn this red bit of paper into a green bit of paper? And the response you'll get is we need to flip it over. And at this stage, I wouldn't worry too much about formalising it. What we're doing is we're multiplying or dividing by -1. But I quite often talk about flipping. So if I flip both sides of the equation, I see x is equal to -2. The final example I had was -4 minus 3x. So -4 add 3 negative x's is equal to +2. So I want to get the x sticks or rectangles or whatever you want to call them on their own. So I need to get rid of the 4 negatives. So I do that by adding 4 positives. If I do something at one side, I do the same to the other. I tidy up my 0 pairs. I've got no 0 pairs to cancel out on this side. I've just got 6 positives. And there are a couple of ways I can approach this now. And I've been inviting pupils to tell me what to do. But the 2 steps we need is we need to multiply by -1. We need to flip. And then we need to get a single x on its own. And this is an opportunity to reinforce what division is, or one of the ways we can think of division. I'm going to split this into 3 equal groups. I'm going to split this side into 3 equal groups. So we can see here that a single x is equal to -2. And these would be the types of examples that I would be doing, I would be demonstrating to the pupils, getting straight into the negatives, because the tiles lend themselves to it naturally. And then I'd be getting pupils to do questions like this. So if you have that website in front of you, you could do those, or if you have some algebra tiles, you could go ahead and try those. The idea of a variable on each side, so this question H here is actually a 4th level question, and the approach can be done, it can be taken there. You can use algebra tiles for that. We just build the expression on each side. Now, you might ask, that's all very well and good, but how do we solve something like this with the tiles? And my comeback would be we don't. Algebra tiles and any manipulative are not about being able to do everything straight away. You can build towards that. I could build an equation like this. So we can see the brackets represented here. We've got x's on each side. You can build some quite complicated things with the algebra tiles. And again, we would just solve this by adding 3 negatives to each side. This idea of a 0 pair, and sort of solving there. I have never actually done this with any of my classes, but I'm just trying to demonstrate the fact that the algebra tiles can be used for more than those sort of level 3 and 4 equations. And we can use them further up the school here. Here we've got the distributive law at level 4 being demonstrated. Again, note the lack of negatives here. I might not necessarily work with negatives when I am using the physical. I would maybe leave that more for the pictorial approach. That's something that we'll see later in these slides. At National 5, I've got the idea of expanding a quadratic. So just a bit of natural progression from the distributive law here, building a rectangle. I have been brave enough there to bring some negatives in. And the completing square, actually physically completing a square using some algebra tiles. The traditional layout below sort of been reflected in the pictorial, the concrete materials above. The distributive law and the quadratics, that's what brings us nicely onto the 3rd thing I'd like to show you. Our primaries have done quite a bit of work with Dean's apparatus, named after I think it's a Hungarian mathematician called Zoltán Dienes. Again, we've got a rectangle been made to represent 13 multiplied by 21. So we've got 13 down this side, we've got 21 along the top. We can count up how many little boxes we've got. We don't always go back to the concrete with our S1s because we find that they're quite adept at this. So we're able to build on what our primaries do. And we might do some sort of examples and problems like the ones below, where we bring a little bit of place value into it. The idea that 26 times 36 will have the same answer as all of these, but the place value changes. The digits will end up in different place value columns. And we find the pupils, if they're okay with the, if they've done work with the physical, the pictorial approach really sort of takes off. And we do sometimes go back to the concrete materials. We quite like doing some division with them. It keeps those primary 7 level 3 pupils on their toes. We find that the ones coming up at level 1 and 2 can really get behind doing this sort of division by building a rectangle here. But the ones that sort of have learnt sort of your rote learning are quite uncomfortable with this. They don't like having their understanding challenged. And it's a case of they often know when doing something like this, they know to carry the remainder over, but they don't really appreciate why. So yeah, it's always worthwhile going back sometimes. The reason we have really moved towards the grid is it goes places. We've had in the past mixed success trying to teach S1s column multiplication. It's often a case of if they can't do this by the time they come up from primary school, a week or two with us isn't going to change it. I have definitely expanded double brackets using the FOIL acronym, and synthetic division for factorising a polynomial. I have definitely taught with that in the past. The problem here is this is 3 different approaches for what is essentially just multiplication. So here we can see a grid being used for the same 3 problems, and hopefully that 3 images sort of sell the story well enough that if I know how to multiply 2 digits by 2 digits in a grid, I can multiply 2 term by 2 term expressions together. And well, if I can multiply with a grid, the division is essentially the same thing, but backwards. And synthetic division is the one I really, I wouldn't say I take issue with, but there is limited opportunity for understanding with synthetic division. Here I have done a factorising question, and I sat down and did this myself. Now, I'm a little bit out of practice with my synthetic division, so what I have done here is I've remembered that I need to take out a common factor from the factor here, but this is not actually the answer. This isn't the what I get when I factorise. I need to take the common factor of 2 out of here as well. And I must admit, I'm not entirely sure why I need to do that. And you think to yourselves, how many times have you seen pupils making that error? The other thing that I would challenge you to think about is what exactly do these 3 values in the middle mean? And could you explain really clearly to pupils what they mean? I also don't like the definition of synthetic, the fact that it's something that's just been constructed. It's not something that comes naturally. So what I do instead is I don't really need to teach them how to factorise. We just build upon the prior learning themselves. And I think this is much more effective than synthetic division. This quote here from Chris McGrain's Starting Points website, I like this part of it here particularly. Synthetic division does not make the easy questions any easier, but it does make the harder questions harder. like this question here, where they're having to find missing coefficients. And if you're bouncing that around synthetic division, you've got P's and Q's being multiplied and added. Pupils will often make trivial, but in the end, mistakes. And the synthetic division, it loses track of what the factor theorem actually is. So this difficult question can be done fairly easily with a bit of substitution. The task I would use is this on the left here, where you would start by multiplying out some brackets, and this would be a bit of revision from National 5, because our Nat 5s would have done this in the maths course. We then gently introduce the idea of doing some division, and really all we're doing is we're reinforcing the fact that those two boxes will give the x squared term, that these two boxes will give the x term, and this single box here will give the x term, the constant term, sorry. And this is something that you would imagine a lot of pupils pick up on at National 5 if they're using a grid. They get into the habit of tidying up their terms using those diagonals. And it means when I come to do this, which might be awkward with my mouse, they don't really need to spend a lot of time stressing on it. They know the 2x cubed from the polynomial needs to go there, because they know their highest order goes there, and then it just becomes a little bit of a puzzle. They're going 2x times what gives me 2x cubed, it needs to be x squared. And then the rest sort of falls from here. That's the difficult bit done. So they know 3 times x squared will give them 3x squared. We don't want 3x squared, we want negative 5x squared. So I need to add 8 negative x squareds on. This means I need negative 4x here, because I'm looking at the multiplication. What times what? What are the two factors I need for negative 8x squared? Now I've got the negative 4x. I know this needs to be negative 12x. But I don't want negative 12x. I want negative 6x. So I have to add 6 positive x's on. 2x times 3 gives me 6x. And then a little check at the end. 3 times 3 gives me 9. And there, we can really clearly see what all of the coefficients mean. We can see that this 3 is 3x squared, which combines with this 8x, negative 8x squared, to give me my negative 5 in the original expression. And I think this is much easier, and there's less, well, there's more understanding. Okay, they're more likely to remember this than, well, I suppose that's unfair. They remember how to do synthetic division, but there's more understanding here, and there's less teaching and less of a leap of faith involved. They can see that it works. And it works at advanced higher, in that I've done some polynomial division here, some long division, and we can see I've divided by x plus 1, and I've got my quotient along the top there. And the remainder is essentially just what do I need to add on to this last term to get my complete expression. And it works for ones of varying complexity. You can see here I'm dividing by a quadratic, and the grid just manages it. You can also use it for working with imaginary roots at advanced higher. Like I've got a picture here from one of my colleagues' slides, and he's used this with his advanced higher class. There may be the worry that in further education, if pupils go on to do maths, that they might have lecturers that use synthetic division. But I would like to think that if we have taken this approach constantly, our pupils will be well enough prepared that it doesn't matter. They will understand how to divide and multiply polynomials together because they've got that understanding built in. The final thing I would like to show you is some work on fractions. I find that a lot of books, the TJ level 1 and 2 books were ones I looked at, And the types of problems we've got here on the left are the ones that the pupils at these sort of lower levels work with. And really, there's no chance to reinforce their understanding of fractions. They're literally just having to colour in one box or two boxes or whatever. And I think this is part of the reason that fractions are a bit of a bogeyman for some pupils. There's not enough chance for them to actually, or we don't give them enough opportunity to actually think about what fractions are. The idea that it's a shape split into congruent or equal areaed pieces. So these questions here on the right, if pupils can answer these on the right, then this means they really have fractions. I mean, the common misconception is this is 1/4, but clearly it's not, because the yellow slice isn't the same as the two boxes on the left-hand side, where we need to cut it up further to create this idea of congruent or equal-sized shapes. And I've got a level 4 question here, which I think illustrates it nicely. So in 4th level, pupils need to do operations with fractions and mixed numbers. And the process for multiplying fractions is really easy. But is that difficult enough to be level 4, that calculation there? And I would say the calculation isn't the thing that makes it level 4. It's the idea, the underlying understanding. That's what makes it level 4. And it's been able to apply that first level, actually knowing what a fraction is. And this idea of 3/4 times 2/5 is a rectangle that is 3/4 by 2/5. So there's a lot of thinking got to go in here to draw this rectangle. The pupils need to realise that one side needs to be 4 long, one side needs to be 5 long, and that we're talking about one whole side by one whole side on the top and the left there. And then they need to carefully think about the rectangle they're going to draw. Because of course, pupils could get the answer right if they drew 3 here and 2 here, and they would still end up with 6 little boxes out of the 20. But, you know, their understanding it wouldn't be there. So it's all about teaching for understanding. You've also got the opportunity to talk about what a 20th is. You know, this idea of we have 20 little boxes making up one whole box. So does any of it really matter? I mean, I wouldn't be saying pupils should draw a rectangle for every single problem they do, but give them the opportunity to develop understanding can help. Because think of how often, I mean, I've got National 5 pupils that will continue to make this error. This idea of we just multiply the whole number and multiply the fraction together. And they don't appreciate the fact that, well, yes, they've got the answer, but they've only got the 2 white bits in this grid here. They've missed off these yellow bits. Again, I wouldn't say multiply fractions like this, but showing pupils that this is how we could multiply mixed numbers just helps deepen their understanding. And I think all of this is needed before we make the jump, or before pupils themselves make the jump to the algorithm, to the shortcut to multiply fractions. So the first level, you know, they might be asked to do stuff like this. Again, I've sort of singled out TJ, but lots of books will just be full of pages and pages of that. I would argue that on the left-hand side, for most of the pupils you have in front of you, that is not a good use of their time. That shading things like the right-hand side into 5, 6 is more useful. And this idea of, again, congruence, splitting each grid up into 6 equal-sized pieces. If the pupils can't do this, if they can't spot 1, 2, 3, 4, 5 out of 6 rows and 5 out of 6 columns and the 5 out of 6 chunks here, if they don't have this understanding, is there any point in them adding and subtracting? and doing anything else with fractions, any other operations. So I think building activities like this in can be quite useful. And this would be one of the tasks that I would do with my first years. We would spend a bit of time exemplifying this, drilling down the idea that each little box in the grid represents a piece of the whole, and an opportunity for lots of chat about what fractions actually are, and then get them started on here. And I mean, we've got the formal layout, we've got the fraction, the common denominator, and then the answer. But the bit in the middle, the diagram, that's the opportunity to build understanding. This idea of we can't add fifths and halves because they're of different sizes, they're different types of fractions. But now in this grid, the grid has changed them into like denominators. And it's this idea of we need 10 of these little boxes to make a whole grid. So I'm dealing with tenths. The idea that I've got 2 grids, so that represents 2 wholes. If I was shading this in to demonstrate, I would maybe then even move these 5 boxes out. I would rub them out and sort of redraw them in the first grid. And we can see the idea that 9/10 would be almost 1 whole. It's almost the full first grid shaded in. So there's lots and lots of opportunity for good discussion and understanding. And a task like this doesn't need to just be basic, because the second side of the sheet moves on some fairly, there's some fairly challenging questions here, particularly the bottom 3 there, where the pupils could shade in any random 10 out of the 15, but what I would be wanting them to do, and what I'm hoping they would appreciate by the time they get to that, is 10 out of 15 is going to be that 10. That's the most efficient way to shade that. And the 6, I'd be looking for them to shade it that way. And again, there's a lot of opportunity for understanding going on there, as well as challenge. Division, well, division's not strictly speaking in the 4th level benchmark. We do some division with them. And again, it's this idea of picking the right sized grid and reinforcing what division actually means. How many times does something go into something else? And you can see here in the first one, I have got 3/5 divided by 1/7. So I have got 1/7 in this 5x7 grid. And I want to see how many times it will fit into my 3/5. And I'd be demonstrating like this. I'd be going, I've got 1, 2, 3, 4, 5 little boxes. So I can fit in 1 group of 5. 1, 2, 3, 4, 5. I can fit in 2 groups of 5. I can fit in 3 groups of 5. Let's get that a bit neater. There's my other group of 5, and then I've got 1, 2, 3, 4, 5 groups of 5. So 1, 2, 3, 4 groups of 5. So again, apologies, I'm using the mouse here. So 1/7 goes in 4 times, and I've only got space for 1 out of the 5th, out of the 5. So I've got 4 and a 5th. And yeah, this opportunity to really develop an understanding of what division is, really develop an understanding of what their fractions are. And I mean, they'll figure out the shortcuts, the sort of traditional algorithms themselves really quickly. I mean, this bottom one here, I've got 2/3 and I want to fit 3/4 into it. I've got 9 boxes, 3, 4, 5, 6, 7, 8. I can't fit the blue box into the red box. I can only fit 8 out of 9. And you will have pupils pretty quickly spotting the 2 times the 4 gives the 8, and that the 3 times the 3 is the 9. there's so much opportunity with a task like this for them to really think about their fractions and think about the problems they're doing. Even as far as what's a suitable grid for this problem, realizing the denominators sort of dictate the grid that they would draw. It's worth noting here that this task I've got here is version 2 of it. I originally didn't think about the problems carefully. I had them working with 24 boxes shaded in and 35 boxes shaded in. The concrete and the pictorial isn't about solving every problem. You need to keep the tasks and the values like manageable. When you do move onto the abstract, you want to avoid nonsense like this. You want to make sure you're keeping the language and layout formalized. So I would be talking to my pupils about the reciprocal and the idea that it's the thing that we multiply something by to get a product of one. And really sort of hammer home the layout. We say we're dividing by 5/7, so we're multiplying by 7/5. And I would be encouraging them to use the proper language. So that's been a bit of a whistle-stop tour of some of the things we do with CPA at Bucksburn. I think those are probably the main ones. So to sum up, why bother? It's not about going back to concrete and pictorial every time you bring in something new, but it is sort of about building up a common language here. So when I did simultaneous equations with my national fives, I took a different approach this where they were used to the idea of a zero pair. So rather than me labouring the point of sometimes we add and sometimes we subtract, I've changed tact for solving simultaneous equations, and I've got them to just create zero pairs by, in some cases, flipping equations or by scaling up and flipping their equations. And I found that that's been quite successful. I haven't had as many silly mistakes where pupils adding when they should have subtracted and vice versa. The zero pair lends itself naturally. I also think engaging with CPA, it's a good way to challenge ourselves as professionals. We keep getting, we keep being told about, how good is our school and standard for registration. And it is part of our standard for registration, the fact we're meant to be developing, lifelong development as we go through the profession. But I find rather than reading, the latest tome from somebody like John Hattie, which I struggle to engage with things like that. I find working with something that's easily actionable, like on the coalface, and is like directly relatable to my subject. I found that I've engaged with this. I've been really keen to engage with it. It's also about giving pupils opportunity for light bulb moments. This idea of building on your prior knowledge, it's all about helping the pupils make connections themselves. And I think one thing that I've been guilty with in the past is, I've jumped to the generalizations straight away. I haven't spent enough time on the pictorial. I mean, the guy on the left-hand side there on YouTube is showing pupils to divide B by 2, to square it and subtract and bring down C. And yes, that algorithm works, but there's absolutely no understanding to what's going on there. And if you get a chance, you should watch this short video by the maths teacher Eddie Woo. So it's Eddie WOO on YouTube, and it's titled Beautiful Visual Explanation of Completing the Square, where he doesn't labour it with tiles and he doesn't spend ages on it, but he just has a little aside to his pupils. He shows them why we call it completing the square. And if you look here, we can see, there's a little blue square and we've got some green rectangles there. He's sort of using he's using a pictorial representation to literally complete a square. And there's a section in the middle. So he says, why didn't anyone tell me this? So him as a professional, you know, he's been able to make this connection himself, but the reaction of his pupils is actually it's quite encouraging, and that's the sort of things you watch the video and you hear them react to it, and you won't have anything quite as visceral in your own classes, but it's quite nice watching pupils and seeing the light bulbs go on, and then being able to tackle some more difficult equations or more difficult problems by using these manipulatives or using the diagrams or by using the understanding that they've built up using those. So hopefully you found that useful. Um, and yeah, all the best in trying some of it out.